So hello, my name is Abdul Dakkak. I'm a senior kernel developer at Wolfram Research. I've been working at Wolfram Research for around 10 years. My title of my talk is Developing in the Wolfram Compiler. So this is the new Wolfram compiler that was released in version 12, and I'll be talking how to extend the compiler and some neat applications that were enabled by using the new compiler. Thanks. So I'm going to be talking about the developing in the Wolfram compiler. My name is Abdul. I'm one of the developers on the compiler project. So I'm going to describe the basic usage of the compiler. I'm going to then describe a little bit of the internals and how developers, and for now, developers are kind of mainly us, but we're going to describe, in the next few releases, we're going to be opening up the compiler to more developers so that people can extend it. And we can use, and then I'll show how you can use the compiler to develop multi-thread code. So there's multiple talks on the compiler. So actually, the Numeric Array just finished. Fahim is going to talk about data feed, Wolfram Finance platform, tomorrow. Tom is going to give a talk on the Wolfram compiler tomorrow, and then Brenton is going to talk about parsing the Wolfram language, which is not really the compiler, but it's related somewhat. So this is an overview of the compiler syntax. You have the traditional sort of function syntax. But one thing you do is you annotate all the input arguments with the typed keyword. So in this case, I'm saying that the arg1 type is an int64, the arg2 type is an int64. And I wrap everything with the function compile, and underneath the hood, there's some machinery to tell you, that tells the compiler that this plus is going to be, an int64 to int64. So one thing is the compiler right now is more optimized, more towards, like we want to build a solid code, a solid platform so that we can generate very efficient code. But as I'll show you, even the current compiler is more generic than the previous version of the compiler. And we've made a lot of kind of interesting progress in the past year. So let me, I don't know. Okay, so the first thing, you probably, if you've used the compiler, is that, or any other compiler, is that you can intermix compiled code with top-level code. So in this case, I'm compiling a function that's doing a random walk. Now I can compile it, and then the results I can use like our visualization technology to do the plot. So in this case, I'm compiling kind of the computationally heavy part of the code, and then the other parts I can just leverage pre-existing techniques, pre-existing code. And that's kind of the design. Is like we want to have a seamless integration between things that are compiled and maybe there's some restrictions, and the rest of the code, which has practically no restrictions. The other thing is, there are some cases where you want to have uncompiled code within compiled code. So let's say there's some codes which it makes no sense to compile. So something like file IO, or in this case, this is getting some entity. So in this case, we introduced in version 12 this concept of a kernel function. So a kernel function takes a function and a type, and then evaluates that kernel function within the evaluator. So in this case, what I'm doing is I'm getting the, I'm giving it a name, and then I'm getting the mass of the planet called with that name. So this is the code that is run within Mathematica, the interpreter, but the rest is actually run in the rest is compiled. So in m times a is a compiled function. Now you can build more complicated examples, but this is a simple thing. So in this case, I'm intermixing even within compiled code. I'm intermixing uncompiled with compiled. There's some sort of layer. So you can intermix on the outside or on the outside of compile or in the inside of compile. Feel free to ask any questions. It's like an hour presentation. Yeah.
What happens if the types are wrong?
Well, user error. I mean, it will tell you, the types are unexpected. It would throw an exception, and then would evaluate in uncompiled code.
You get errors if
Right.
you can't compose things. And actually, we've been improving the quality of messages, and now you're starting to get quite useful information.
Right.
I'll show some of that tomorrow.
Yeah.
And with this kernel function, that would happen at runtime.
Right. Yeah.
The kernel function returns a result, and if it returned a result that wasn't expected, you said the kernel function returns a string and it returned a Boolean.
So.
Then you would get a runtime.
Right. So here's an example. So in this case, this quantity magnitude or entity is giving you an arbitrary precision float. So the way around that I did was I said set precision to machine precision. But let's say I didn't do that. And in fact, I was not doing that. And I evaluate this. Now, it's a bit hard to read, but it says a compiled code runtime error occurred, reverting to uncompiled evaluation. So it's still giving you correct results. It's just this real 64 was not satisfied at runtime because the result was not a real 64. It was an arbitrary precision arithmetic.
Sorry just to butt in again, Abdul, but generally, runtime errors are bad, compile time errors are good.
Right.
Yeah, you agree? Yeah. We want to catch errors when you compile the program because you do that once. You don't want errors when you're running. And the whole point of a type system, one of the important things of a type system is to reduce the incidence of runtime errors. Mm-hmm. Sometimes they're hard to use domain errors and things, or calling to other systems, but that's
right.
Sorry, go.
That's right.
Is there a nice way to prevent it from going to the
yes.
Going to the
yes. There is.
Yeah.
Because if I type proof with the small e, obviously I wouldn't want to.
Yeah. Right. Also, these examples are meant to fit on the screen. There's you wouldn't you'd have more complicated programs, and obviously you'd need better you need more informative errors like Tom was saying for that. So here's another sort of feature of compiled code, and that's they're abortable. So here is a fairly complicated way of writing an infinite loop, and the reason is people probably write these things. I mean, and then they fix them, and then but I can say, okay, function compile and then a while loop, and this index is never what is the problem? This index is never like even or but I could say, okay, evaluate this with a time constraint of 0.5 seconds, and if this code takes more than 0.5 seconds, so it aborts. So that's kind of another feature, is that you can abort these evaluations, or if I do what? Why is this doing that? That's not what I want. Sorry. Okay. So if I have, this thing is evaluating infinitely, and if I do, command dot, or on Windows it's control dot or something, you would get aborted. The other kind of interesting feature, and this is something that I had trouble with the old compiler, is that these compiled functions are now composable, which means I can construct a function, and then I can pass that as an argument to another kind of compiled function. So in this case, I'm defining a mapper function, which is just does a plus 2, and I'm going to define my own map function, which essentially just for every element of the list, it's going to apply that input. It's going to take an f and then input list, and for every element of that list, it's going to just apply f to it, and it's just going to return some result. So then I can essentially I can call that my mapper function with range of 10, and I would get that result. So I can build more complicated programs, or I can pass in functions around, or I can return functions from compiled functions, and so on. So which means you can express more complicated programs, and you don't have to have one big piece of block of code that contains all your programs. The other interesting thing is that compiled code supports strings. The bytecode compiler only supported real, complex, Boolean, and integer, and the list versions of all of those. But the new compiler supports strings. So this thing just says, give me count the number of letters in a string. It only works for lowercase letters, but I can then say, okay, give me the letter count of the Declaration of Independence. So it has the letter counts for A, through Z, and then the last one is the other. If something is not a lowercase letter, it just puts it over there. Now, one byproduct of that is also that you can do print. I can do print of res, and evaluate that, and it would do a printing of the list. So in this case, it's kind of more it's printing that it's a packed array, a rank 1 packed array of length 27, and it has that content. Or I could do sort of print of anything, or even because of the integration with the kernel, you can even do echo. So that's the echoes thing. So the other thing is that compiled code supports expressions. So this is, you could do arithmetic on expressions, so symbolic kind of evaluation. So in this case, I have a function that takes two expressions, A and B. And A and B are, could be any Wolfram expression. So I can put a, let's see, graphics disk or something. M times the disk. So this is still compiled, but you can use that sort of stuff. And actually, the application of this might become more relevant when Tom shows the data structure and sort of iterator code.
Is there any speed benefit that's implemented? Those kinds of things?
Yeah. So in this case, you could actually go around the evaluator. So you can. So in the Mathematica kernel, each let's say plus is there's a function, a C function called plus that the evaluator eventually reaches into. But through this mechanism, well, this is a times. So eventually it would reach some C times that works with arbitrary expression. So this thing is just going around the evaluator and just calling that times directly. So there is some speed benefit. Now, obviously, it's not the
It's a complicated question, though. There is not a single.
Right.
There's not a single answer because it does depend upon the details of what we're doing.
Right.
It's not a magic bullet to just suddenly make your code run itself.
Right. And probably like for simple things, it won't be faster, but there are cases where you actually want to use this, and if you did not have, even if it's slower, even if it's 10 times slower, if the surrounding code is 1,000 times faster, but this is the blocking thing, then you would want, even if it's slower, you'd want that sort of feature. That's kind of the answers. There are features that would enable other speedups.
Okay, that sounds great, but I'd love it even a Donkin example of when that would have been the case. I tend to run for tens to hundreds of hours, and so if you told me I can do 20% speed up, well, that helps me a lot under certain circumstances. What would those things be?
Well, I don't know what the
Chat with us afterwards, or
right.
and let's look at some details of what we're doing.
Right. I mean, I'll show some speedups results. In fact, this slide will show something. So the other thing is in version 12, or definitely in 12.1, there's these numeric arrays. And numeric arrays are essentially generalization of these packed arrays. So arrays that work on all the C scalar data types, so like int 8 and unsigned int 32 and real 32, things like that. So in this case, so the compiler knows about these things. So you can just say, I have a list that's a numeric array of real 64, and then I can define a moving average. So a moving average, you take, in this case, it's just looks at 3 elements. It's just a convolution. This is just a sort of a convolution type of thing. But it's looking at 3 elements. It's handling the case of, is it at the beginning or the end? And I could do the evaluation, and I get the correct results. So I can just pass in a numeric array, range of 10 of real 64. I would get that result. Now, we're still adding support for these numeric array for a bunch of functions, but moving average is not one of them. So you get an error. So you'd have to use these packed arrays or other sort of code. But if you do the comparison, so the top one is using the native moving average. Now the moving average is a lot more generic. It takes a lot of parameters and a lot of functions. In this case, I'm just having a specialized version. But the top one is showing it takes 0.1 seconds for these 10,000 elements, and my code is taking 0.003 seconds. And I can make a plot of the results, so I can just evaluate this over 1 million elements for the both the top level moving average and my implementation of moving average. And I can make a plot. And this is like a log. This is a log plot. So the blue line is the built-in one, and the yellow line is the compiled one. And this is like 10 to the minus 6, and this is 2 times 10 to the minus 5. So it's a log plot. So this at this point, it's taking like let's say 10 to the minus 4, but this one is taking 0.01 seconds. So there's like a huge speed up, 100, 200,000x. It sort of grows. So take that with a grain of salt, because I'm building a specialized piece of code, and I'm comparing to a more general case. But let's say I wrote optimized C code, and I compare that to handwritten compiled code. So this is, the red ones are C, the blue ones are compiler, and this is from a few months ago. So we're actually better in the other sort of scenarios. But I wrote Mandelbrot, for example, and we're about the same as handwritten optimized C code. Same thing for a Gaussian filter. If you actually compare, I have to ask, I wrote a C version that's using MKL, and I compared it to our version, and we're faster than the MKL. Both are using MKL. It's just we're specializing. We have more flags or something for the MKL. Histogram is the same sort of speed up. So this is the sort of speed up that if you were to write, this is the kind of the target speed up. You're comparing against C. You're not comparing really to top level. So how we achieve that? So internally, we go through the compiler is a complicated thing, but we go through a multi-stage pipeline to make it more manageable and understandable. So we take this Wolfram expressions or abstract syntax trees, and we do some transformations to make it simpler. We call that a desugared AST. So there's it's a subset of the expressions. Then we go to this intermediate representation. So this is something like assembly, but it's system agnostic, and it's untyped. So we have this untyped IR. Then we do some type inference. So we try and fill out what the types are for that IR. Then we get this typed IR, and then we generate an executable. And there's a lot of optimizations that are happening at every stage of this sort of process. So let me kind of give you an overview of this. So let's say I have a function, and this is the running sort of function that I'm going to be using. So I get an n, and then I do a do loop that just increments up to n, and then I return the result. So it's kind of a not interesting function, but it produces, it's a proxy. So the first thing that we're going to do is we're going to do expression analysis and transforms, and what you're going to get out of this function is a new, what you're going to get out of this expression is a new expression that has the same, it's still a valid mathematical expression, but it replaced the do loop with a while loop. It did some optimizations like the increment became a plus, and it's doing like saying, I know this number is will never overflow, so I could do arithmetic in a certain mode and things like that. So this is a sort of operations that when we take a user input, we translate it into this sort of form, and we annotate properties on that sort of expression so that so that we are able to kind of correlate back to the original input form. Then we take that sort of expression and we go through this what we call lower form IR or this untyped IR. And what you get is again you get a data structure, but I'm just presenting it as a textual form, where every node, you get a graph where every node is a linear sequence of instructions, and there's edges if there's like jumps. So if conditions and loops, they become jumps into other sort of linear execution instructions. This is not something that people want to read, or essentially this is something that the compiler developers are interested in, but not really for the general public. Now we then do optimizations, and if you notice this complicated, well, this is not super complicated, but there's a lot of instructions here, and we compress that, or we optimize that into this sort of program. And this is the minimal program that you need to execute the code correctly. And then finally, we use backends such as LLVM to generate more system-specific intermediate representations. And this, again, is a much lower level than our Wolfram IR, but it's closer to the final assembly. And then finally, we generate assembly code. This is x86 assembly. that performs the operations. And this becomes, if you just, I had to cut this, but this becomes quite long quite quickly if you have, complicated, I mean, even like, 5 nested loop, no, not 5, like, just like 3 nested loops, and, when you're looking at like these data structures that, Tom is doing, is just like, 20 pages of thing, and it just tells you, and you have to debug it or stuff like that. But because we have a pipeline sort of algorithm, every sort of stage we can actually inspect what's exactly happening, and we can isolate that. So let's say if something is deleted or something got corrupted, we're able to figure out why it happens. We also have like some sanity checks internally for the compiler developers, so that you don't delete a function that's actually called and things like that. So we have an internal linter. So this is kind of the high-level workflow of the compiler, and you can add extra things, extra components in at each level. But I'm going to talk about two more high-level things that you can actually add into the compiler, and that's you can extend the type environment. So let's say I want a some special function that's not in the compiler. You can add that, or you can say, my new primitive is just a syntax trigger for something a bit more basic. So something like up to is a syntax trigger for something like if the length is less than n, do something, otherwise do something else. Or nothing is another example. It just deletes the thing. And this is very low-level syntax. It's probably not going to be exposed this way, but I can show you how you could do it. So let's say I want to add a new type. So I'm not happy with whatever types. I don't care about int64. I want int64 modulo 24. So I can do operations on that type. So I can say, okay, I'm going to define this type int64, or I'm going to define a function that I'm going to define a binary function. It takes 2 int64s and returns int64. And I'm going to define the plus and times on that. Now, actual plus addition, I'm just going to do it in int64, and then I'm going to do the mod, and then I'm going to cast back. So this is like a C type of casts that you could do to kind of tell this to use the integer plus, but then I'm going to define sort of a wrapper around that. And then I'm going to define that I have a new Sorry. Why did this not? Just give me a second. Fact. Okay. So I'm going to define a new type called int64 modulo 24, and I'm going to define new functions plus. That's going to call my plus function that I defined previously, and then times. And then I can essentially write a times b plus b, plus a times b, some expression, and I can then generate code from that. So this is the I can generate a program from that. Let's see if I can zoom out of this. But it defined when it goes to the operations, it's calling this my times in64 module in64, and that's defined as a call to the runtime function that does a binary plus, and then it's doing a sort of a mod as well. Actually, it's a binary times, and then it's doing a mod. But essentially, I can define kind of arbitrary functions on that. Now, to execute this, I need to tell the code generator that generates the assembly what does in64 means, but I'm not going to do that in this case. Right? And then, other than adding types, you can also add functions. So I have a function here, which is a Euclidean distance. So it takes x and y coordinates, and these x and y coordinates are defined for any type. So this is saying for any type A, this function takes 4 A's and returns an A, and then I can just define that. I can then add a function called myDistance, which has that implementation, and then I can define like a nearest type of function. So this nearest function is just saying I'm going to get a point and a point cloud, and I'm just going to go through all the elements and find the smallest, the point with the smallest distance. So I can just kind of do that and get the results. Right. So I get the results as the output. So you can essentially add your own function and extend the compiler if something is not supported. And this is how we actually develop the compiler. So we try examples. There's some things that are not supported. We add an implementation, but we add everything in top level in the Wolfram language. So you can also add functions that reference external libraries. So I think Fahim is going to show a more complicated example of that. But in here, I have a function that I want to call the libc sign on it. But you can have a function that you can implement something like library link on top of this. You can have a refer to an external function that has such and such a name, and you provided the name and the type, and then you can just call it. So this is calling the sign function from libc. Now the other stuff is you can go even further. So you've already written into C. Well, what happens if I want to write assembly? So so I'm not going to show how exactly you write that, but this is a CPU ID instruction in assembly that is implemented. And what this thing allows you to do is get some parameters from the CPU. So for example, in here I'm saying, does it support SSE3 or these vector instructions version 3 on this machine? And you can kind of, in here, you can see that it's calling some assembly, and these are the assembly instructions that is calling. So it's embedding assembly in sort of the low-level implementation. So you're actually intermixing assembly with Mathematica. So you can go from expressions down to assembly. Right. So the other way of extending the compiler is by adding macros. So this is, if you have a function that's just syntax sugar for something a bit more primitive, then you could do that. And there's a lot of functions that are essentially can be decomposed into while loops or variations of that. So here I have a function which I want to define Horner form for it. So Horner form is not known to the compiler. And so it's just saying Horner form, and it has the power and things like that. Now, one thing you could notice is that there's an x to the power of 2, and there's already a macro in the language that says x to the power of 2, or anything to the power of 2 is just you multiply the thing twice. You multiply the thing by itself. So in here I have an x, and then I sort of multiply that. Now, I can say I'm going to register this Horner form. Now, for the sake of demonstration, I'm just going to take a special case of Horner form. I'm not going to show, the recursive definition, and it matches exactly what I have in the previous, example. But I'm just going to take the Horner form, and you can specify the patterns that you want to capture. So I have a coefficient, third coefficient, to the power of 3, and I'm just going to expand that to the Horner form. And now Horner form is known to the compiler. Well, it's not known to the compiler. It's known. It can accept to the Horner form is acceptable to the compiler. So it let's see. So it desugared that function into this function. So it's 2 plus 7 times x times some other things. I think the parentheses are not showing, but they're there. So that's why I was doing this to print. But you have this module times this sort of expression. So there's other new features that we're going to be adding, or we want to add to the compiler and to the language in general. And one is data structures. So see Tom's talk tomorrow. And there's also parallel evaluation. So I'm going to talk about parallel evaluation in the next few minutes. So what you want to write in parallel evaluation. So Mathematica already has a thing called parallelize, parallel map. Yeah.
Just one small question regarding the previous slide.
Sure. Yeah.
You showed the macro system with sort of pattern matching. Is that the pattern matcher? Can I use patterns there?
You can use patterns. I mean, it's an implementation of the pattern matching. It's not the kernel pattern matching, but
It uses the same
So condition,
yeah.
test, all this is going to work?
It doesn't support everything, but it supports what's needed for.
Right. Pattern test works. Condition works. So those two cases, blank sequence, flat orderless, that's not supported. But default value, I mean, I think 90% of the cases, if there's ways around, if you want orderless or flatten, you might have to go into a more manual process, but you could do the transformation just not using the macro system. You could do AST sort of transformations. So in I don't know, since before I joined, so there was already a parallel evaluation system. So you essentially say, I have a function, I want to parallelize the map function, and it would work. And it also, this thing worked on not only multiple processors, but it also works on multiple machines. So if I have a cluster of machines, I can then say farm out this function to a bunch of machines and do the evaluation. But one of the problems is it uses multiple processes to do the evaluation rather than multiple threads. And what that means is, that's something that parallelize uses multiple processes, but also there's another thing, which is users are not able to write multiple threaded code. So people want to write, regardless of parallel map or parallel table, people want to say launch this thread or launch this task, split this, in parallel or in the background, and then join that later and things like that. So people cannot write that in top level, but you could do that in the compiler. So in current Mathematica, the way parallel evaluation works is that, and this is not the implementation, this is what I think the implementation is. So if I do parallel map, what it does is it would launch a bunch of kernels. It would then distribute the definition of that function, the input function, to all the kernels. It would then partition the data into the number of kernels that were launched. It would submit the program with that chunk data into all the sort of subkernels. It would wait for all the jobs to complete, and then would just return you the results. So pictorially, you take a list, you evaluate parts of that list on a bunch of kernels, and then you wait, and then you get the result. Now, there's nothing wrong with this. In fact, that's like how parallel evaluation works in general. But the problem is that it's doing this in multiple processes, and it has to copy data. It cannot work on things in place and things like that. So what in practice happens is that these sort of submitting jobs and waiting, aggregating results becomes a huge bottleneck. So you cannot work in place. You cannot share that list or give something a view of the input array. So what we want is to essentially have same idea, just I want to have the list to be shared between the two, and the results can just all write into the same location rather than copying data from multiple processes. So it's relatively trivial to write this as an AST transformation. So it's not super complicated. I mean, it fits on the screen. But what you could do is just say, OK, I'm going to just do the same operation, but instead of launching kernels, I'm going to launch some threads. I'm then going to create a view of that array. So what a view is, essentially, it's a window of the array. So it's, in this case, it's like a read-only kind of view. Well, it's a read-only, like, essentially you have the same underlying data, but your indices are essentially shifted by a certain position. So let's say I have let's say I do a partition here. Actually, let me sort of go up a little bit. So if I do a partition, I want a view might be same underlying data, but the index 1 starts over here. So these data are shared, except when I index into this, 1 just points to this, and then 1 in here points to that. So this is like a view partition. And there's a bunch of languages that have this sort of feature. But I can create that so that I don't incur a data copy sort of overhead. And then I can essentially say submit a new function that feeds in that list view into each thread, and then I can join the threads and then return the output. And what that means is I have the same sort of figure. There should be an arrow over here, but it's the same figure, but now I'm using, instead of multiple processes, I'm using multiple threads. And all the data is shared. So in here, I have a shared view of that list, and I don't do any extra mem copy or any sort of operation. Now, we can implement that. So in this case, this is a dummy example that just does nothing useful other than it does some work. Why is that?
When you launch multiple kernels, there's a licensing structure.
This doesn't require.
This is not launching multiple kernels.
Sure, but how does the
Uh, what is this like that?
This isn't launching kernels, this is launching threads. This is one kernel.
Right. So this is,
That's the whole point of this, is using threads in one kernel, similar to the things Mark was showing.
So they have to be local.
So this is local. That's the whole point.
Just a pure SMT shared memory is not distributed.
right, this is not distributed.
This is in one process using multiple threads. This is a new way to do parallel computations in core.
Right.
Include like multiple kernels and multiple threads within each kernel.
That's what I was.
In theory.
Well, but
On the same machine, that starts to do this.
Not on the same machine.
right. On different machines, that's kind of what you.
It's possible to make a hybrid thing where you, but with hybrid things, it's usually good to make the base cases work first, and then make the hybrid scheme work.
Right.
Anyway,
So this is a function that just does a loop in the middle, and then I have a parallel do that it just iterates 1,000 times, and I'm using a parallel do instead of a do in here. I could also do parallelized do. Now, if I launch my, let me show. Wait, how do I? So I need to. So I need this thing, right? So right now, is there a way to clear this? Okay, well, I don't know how to clear it. But I'm sort of idle. These are the 4 different cores. I have 4 cores, and there's hyper-threading, but I disable those. But it's not using all 4 cores right now. Now, if I do the parallel evaluate, you can kind of see a tick. But if I increase that, problem is increasing that means the other parts become slower. So I made it 10 times slower. But it's doing. You can kind of see it. It did use multiple threads in here, so kind of see that. So let's kind of go back and then compare. Am I actually doing parallel sequential? So I have the same code, except instead of a parallel do, I just put a do, and then I can evaluate that function and get the parallel timing. So before it was 0.8 seconds. Now it's the sequential is 1.85. Now, if you do the parallel do function, so just without so I'm just calling the parallel func without this function compile. It takes about 73 seconds. But if I essentially decrease the originally I have 1,000. If I decrease it to 100 because of, we're not going to wait a minute. It takes 4.5 seconds to do the traditional way of performing evaluation. So you're getting, again, you take this with a grain of salt, but you're getting from 73 to 100x speed up. Type of benefit. So I think that's pretty much it, unless there's any questions. Yeah.
I have code that uses large integer modular arithmetic.
Sure. Yes, but I mean it's.
You have to buy lots of beer or wine or cheese.
Yeah. So definitely we're constantly expanding.
You want large integers and you want modular arithmetic on large integers. Because our modular arithmetic works 3. So
that would be a starting point before we get a chance to work on it.
Yeah.
So, you called libc sign in one of your examples.
Mhm.
Is libc some sort of magic string, or is the because Macs don't have a libc.dilate, right? So,
Well, it's saying. I mean, I can show you the implementation. It's
You don't need to link the library.
right. You don't need to link the library.
Yeah. So you don't link the C library. It's already linked in because this is
Right.
written in.
So
Right.
this is
right, but I presume if you're linking in some random function from some random library,
Then you would have to give a name in the compile, function compile. You give
right.
the name of the library.
So an example is the parallel stuff is using OpenMP, the OpenMP runtime. And if you look at, some of these are a bit hairy, but let me see if I can find a simple definition. So this thing. So I'm giving it a pretty name called OpenMP RTL begin, but underneath,
declare the name and then
you tell it what's the external function name and what are the types. But if the function is already in the kernel, OpenMP is already in there, you don't have to tell it the external library. But if it's not, you tell it, load the library from such and such location. And that's kind of like how some of the sort of.
So the libc is really just a convention that we've adopted for these
Yes,
kinds of symbols.
that's right. It's quite useful to call the libc library.
Right.
Right.
Yeah, I mean,
You can imagine.
So for example, Printf.
That's
You-
more complicated.
Right. Printf is complicated. But you want to call it because it's you can kind of say it's thread safe or some sort of thing. But so it's sometimes useful to print stuff to debug.
Let me also say, when you run the compiler in the cloud, some of these things are disallowed. So you can't call random functions in libc
Right.
when you're running the compiler in the cloud, because you might do like
File I/O and stuff.
You might violate the
Sandbox.
You can't run
Assembly.
assembly when those features are not enabled. So if you want to connect to random libc functions, then you either buy EPC or you run it in a local copy. So
Right.
you can compile it, you just can't run it.
Yeah.
So continuing the topic there, so you showed the libc functions. What about like functions from C++ from STD, for example?
Well, the problem there is you have to figure out what they're called.
Well, also no. That's not the problem. The problem is you need to instantiate them. How do you instantiate them? I mean, which functions first of all? And Well, vector is not it's a data structure. You can write a wrapper around this, C wrapper, and then export it. So I think we need to go, but please, there's a question.